Welcome to the Explainer. Today, we're going to dive into a couple of problems that, on the surface, seem pretty complex, college level stuff. But they're going to help us uncover a really surprising secret about how the world actually works. It turns out, so many of the systems we deal with every day are governed by a kind of hidden language. So let's kick things off with a puzzle. Just imagine this. You're in charge of this huge gaming tournament. It's packed, but the schedule, it is a complete and total mess. Games are overlapping all over the place, and you've only got a limited number of computers. So how in the world do you figure out the absolute bare minimum number of machines you need to pull this whole thing off without it turning into total chaos? Now, you might be thinking, oh, that's just a scheduling problem, better time management. But the answer is actually way, way deeper than that. The real solution lies in learning a powerful mathematical language, one that's specifically designed to map out connections and show us answers that are otherwise completely invisible. Okay, let's really get into it. So this first section is all about that language. It's a fascinating and you'll see a surprisingly visual field of math called graph theory. It sounds really complicated, right? But the core idea is incredibly simple. You just take a bunch of things, could be people, could be places, or in our case, video games, and you represent each one of those things with a simple dot. We call that a node. Then you just draw lines between them, which we call edges, to show how they're connected. And that's it, seriously. That's a graph. And this abstract idea, it maps directly onto the real world. I mean, think about your favorite social network. It's just a giant graph, right? People are the nodes, and the friendships are the edges connecting everybody. A roadmap? Same thing. Cities are the nodes, roads are the edges. And, you guessed it, our messy tournament schedule, we can turn that into a graph too. So how does this actually help us? Let's take this new language of connections and apply it directly to our gaming tournament puzzle. Okay, so here's our problem in table form. And wow, it is messy. You can see the overlaps all over the place. Fortnite clashes with Dota and Rocket League. Rocket League seems to clash with just about everything. Trying to figure out how many computers you need from this is a real headache because it's almost impossible to see the whole picture of all the conflicts at the same time. So here's what we do. We translate. Each game becomes a node, a dot. Then for every single time clash we saw on that messy table, we draw an edge. And that line, that edge, means something super specific. These two games absolutely cannot run on the same computer at the same time. And just like that, our scheduling nightmare becomes a simple visual map of all the conflict. Now, once you have the graph drawn out, the problem basically turns into a coloring puzzle. The rule is simple. If two nodes have a line between them, they can't have the same color. So let's say we assign Fortnite to computer 1, our first color. Well, since it clashes with Dota and Rocket League, they can't be on computer 1. So Dota gets computer 2. But now look at Rocket League. It clashes with both Fortnite and Dota, so it needs a third color, computer 3. And by just following these conflict lines, we find out the minimum number of colors we need is 3. It's amazing. This visual graph made a totally invisible problem perfectly solvable. But this whole language of connections isn't just for one-off puzzles like that. Let's see how it applies to a tool that, well, millions of us use every single day, spreadsheets. You ever stop and think about what's really happening under the hood when you change one cell and, like magic, a dozen other cells update instantly? Yep, that's also a graph at work. You can see right here, the formula in cell B1 directly depends on the value in A1, A2 depends on B1, and so on and so on. So the really key idea here is dependency. The connections in this case aren't just simple links, they actually have a direction. Information flows in one specific way. A change in one cell sets off this cascade of updates down the line. And of course, we can visualize this whole thing by drawing a graph, but this time with arrows instead of just plain lines. An arrow pointing from cell A1 to B1 shows that information flows from A1 to B1. And this dependency graph, well, that's the hidden map that the spreadsheet software uses to know exactly what it needs to recalculate, which is what makes it so fast and efficient. Okay, so far, we've seen how graphs can describe the hidden structure of digital systems. But what about the physical world? The one all around us. Well, it turns out there's an entirely different but just as powerful mathematical language for that. So let's think about a new problem. This time, it's not about connections or dependencies. It's about physical shape and form. An architect needs to design a perfect, structurally sound arch. Now, the architect has a really specific set of rules to follow. The arch has to be exactly 20 meters tall, it has to be a perfect parabola, and it needs to hit a very precise width at a specific height. And these aren't just, for looks, they are absolutely critical for the structure's integrity. The language for this problem isn't graph theory, it's algebra. By translating those physical rules into a quadratic equation, the architect can define the perfect curve of the arch with absolute pinpoint precision. This one single, elegant equation has all the information needed to build it perfectly. I mean, isn't that incredible? So what have we really seen here today? We've gone from scheduling a chaotic gaming tournament to understanding how spreadsheets think, to designing a massive physical building. And in every single case, the fundamental tool was the same: translation. And that's really the big takeaway. Math isn't just about crunching numbers. It's this powerful collection of different languages that give us the ability to describe, to understand, and even to manipulate the invisible patterns that are all around us, whether those are digital connections, logical dependencies, or physical curves. And that leaves us with one final thought to chew on. Now that you know about these hidden languages, what invisible structures are you going to start seeing in your own world?